In the depths of darkness, the mystery of the black hole. Within the cosmic ripples, time's waves ceaselessly roll. A place where light is trapped and sound is lost. In the heart of that darkness, the flame of theories exhaust. Beyond the horizon, where space and time entwine. When the doorway to time opens, past and future align. As starlight races through the tunnels of time, the night sky of yesteryear unfolds in sublime. The heralds of the future seep through the cracks. Traces of destinies foretelling, mysteries from the tracks. The enigma of the cosmos, the song of the blue planet. Whispers of the stars, the secrets time can't forget. Journeying at the speed of light, a cosmic existence. Dancing through the ages, the universe's heartbeat's persistence. Entwined in the threads of fate we find. Flowing through the cosmos, the ever-expanding time. The pupil of the black hole, the gateway to time travel. Captivated by those mysteries, we run towards dreams unravel. Today, we will serialize the 16th lecture of the introductory course on astronomy, covering black holes and time travel in 3 parts. Subscriptions, likes, and notification settings greatly support video production. The concept of a wormhole, referred to as a bug hole in Dr. Stephen Hawking's writings, is a hypothetical concept based on Einstein's general theory of relativity. According to Einstein's theory, gravity represents the curvature of spacetime. Therefore, in regions of strong gravity, spacetime is warped. If spacetime is warped enough, it may give rise to a wormhole, connecting 2 distinct spaces. A wormhole, or bug hole, is a narrow and elongated passage connecting 2 points in space. Similar to a bug traversing an apple and reaching the other side faster than going around the surface, a wormhole might allow transcending time and space more efficiently. Dr. Hawking explained the concept of bug holes in his book A Brief History of Time. According to Einstein's general theory of relativity, strong gravity corresponds to the curvature of spacetime. In quantum mechanics, spacetime is quantized, composed of continuously small particles. Bug holes could be explained by combining these 2 theories. If the curvature of spacetime between 2 spaces is significantly warped, and this curvature is smaller than the size of quantized particles, a bug hole connecting the 2 spaces could form. Dr. Hawking suggested several possibilities if bug holes exist. Travel to other universes. Aid in understanding the origin of the universe. Possibility of time travel, travel to the past or future through bug holes. Possibility of interstellar travel, travel to other universes through bug holes. Movement of energy and matter, transfer of energy and matter through bug holes. Dr. Hawking also proposed that bug holes could open up the possibility of time travel. If one could travel to the past or future through bug holes, time travel becomes feasible. However, the existence of bug holes remains a theoretical hypothesis. If bug holes were to exist, they would need to satisfy 3 conditions. Sufficient warping of spacetime. Stability of the entrance and exit of the wormhole. Ability for matter to traverse through the wormhole. Connecting 2 distant spaces. Can occur in regions with strong spacetime curvature. May open up the possibility of time travel. Nevertheless, the existence of bug holes has not been experimentally verified, and many aspects of their characteristics remain unknown. While Dr. Hawking opened up the possibility of the existence of wormholes, he also issued a warning about their potential dangers. If one were to travel to another universe through a wormhole, there is a risk of not adapting to the laws and life forms of that universe, leading to potential hazards. Additionally, altering past events through time travel could result in unforeseen consequences in the present and future. In conclusion, wormholes are a fascinating concept with the potential to exist in the universe, but their associated risks should be carefully considered. Dr. Hawking emphasized the need for caution when exploring the possibilities offered by wormholes. The existence of wormholes remains a mystery, but it is anticipated that, if proven, they could play a crucial role in advancing our understanding of the universe. In black hole theory, the event horizon refers to the region surrounding the singularity at the center of a black hole. Crossing this region means reaching a point where not even light can escape from the black hole. The event horizon determines the size and shape of the black hole, varying based on its mass, charge, and angular momentum. The information paradox in black hole theory arises when applying both general relativity and quantum mechanics simultaneously. It revolves around the question of whether information about the matter consumed by a black hole is forever lost or preserved in some way. According to general relativity, a black hole, as per the no-hair theorem, carries no information except for its mass, charge, and angular momentum. Consequently, it should emit Hawking radiation unrelated to the initial state of the ingested matter, eventually evaporating. In this scenario, information about the consumed matter appears to be permanently lost. However, according to quantum mechanics, the state of a physical system is determined by a unitary operator, and since unitary operators have inverse operators, information must always be conserved. This implies that information about matter consumed by a black hole should somehow be encoded in the radiation emitted by the black hole. The conflict between these two theories results in the information paradox, a major topic in the field of black hole thermodynamics. Various solutions have been proposed, such as attempts to prove information preservation through the holographic principle or ADS/CFT correspondence. Black hole theory remains an incomplete field requiring further research and discoveries. I will now explain the holographic principle and ADS/CFT duality related to black hole thermodynamics. The holographic principle suggests that information about the volume of space can be encoded on the boundary, such as the gravitational horizon of that space. This principle originates from the Bekenstein-Hawking formula, stating that the entropy of a black hole is proportional to the area of its event horizon. This implies that information about the objects consumed by a black hole is encoded on the surface of its event horizon. The density of this information surface is limited to Planck units, known as Planck bits. ADS/CFT duality posits an equivalence between the reduced string theory in anti-de Sitter space, ADS, and a conformal field theory, CFT, at the boundary of that ADS space. This duality provides a non-perturbative formulation of string theory and is considered a significant development in both string theory and quantum gravity. The utility of this duality lies primarily in strong/weak duality pairs, making it mathematically more manageable when quantum field theory's strong interactions correspond to the weak interactions of gravitational theory. The holographic principle and ADS/CFT duality play crucial roles in resolving the information paradox in black hole theory and in constructing theories of quantum gravity. Additionally, they provide powerful tools for studying strongly coupled quantum field theories. The holographic principle and simulation hypothesis are related theories. The holographic principle suggests that information about the volume of space can be encoded on the boundary, such as the gravitational horizon of that space. Proposed to address the black hole information paradox, it implies that information about matter consumed by a black hole is encoded on the surface of its event horizon. The simulation hypothesis posits that our universe could be a simulation of some intelligent entity, with the existence of minimum and maximum units in the universe. It is associated with the holographic principle as both theories involve limits and phenomena reminiscent of quantum mechanics and computer operations. In other words, the holographic principle proposes that the universe is a 2D projection, while the simulation hypothesis argues that the universe is a simulation run by a computer. Both theories fall within the realms of physics and philosophy, presenting hypotheses that are challenging to scientifically validate or refute. Regarding the fate of an object falling into a black hole, the answer to whether it will undergo complete collapse is as follows: an object falling into a black hole does not undergo complete collapse. An object beyond the event horizon of a black hole is drawn towards its singularity due to the black hole's gravity. The singularity is a region where gravity becomes infinite, and spacetime is warped, violating known physical laws. Therefore, An object falling into a black hole will exist in some form at the singularity. Hawking radiation is the energy emitted from the singularity of a black hole. It arises due to quantum effects, and as the black hole's mass decreases, it emits this radiation. Hawking radiation is not emitted as a thin beam but is composed of various particles such as photons and neutrons. While there is a possibility that an object falling into a black hole could be expelled through Hawking radiation, it does not necessarily mean it will exist solely in the form of Hawking radiation. In more detail, an object falling into a black hole may exist in two possible forms at the singularity. Information form. The black hole does not violate the law of information conservation. Therefore, information about the object falling into a black hole should be preserved at the singularity. However, the nature of this preserved information in the region where known physical laws do not apply is yet unknown. Material form. The black hole emits energy through Hawking radiation as its mass decreases over time. Consequently, there is a possibility that material could be expelled from the singularity at the moment of the black hole's complete evaporation. However, whether this material retains the original form of the object falling into the black hole remains uncertain. In conclusion, the specific existence form of an object falling into a black hole has not been conclusively determined. It is anticipated that further research will provide more information on the nature of these objects through ongoing scientific exploration. An object falling into a black hole does not undergo complete collapse, forming a thin stream like Hawking radiation that doesn't escape. As the object approaches the black hole, its size diminishes and compresses due to the immense gravitational force. During this process, the object's energy is converted into heat and kinetic energy, emitting from the black hole, a phenomenon known as Hawking radiation. Hawking radiation plays a role in gradually reducing the mass of the black hole. If the mass of the black hole decreases sufficiently, it could eventually lead to the complete evaporation of the black hole due to Hawking radiation. However, an object falling into a black hole does not completely collapse into a thin stream like Hawking radiation and doesn't get expelled outward. The information of the object is stored inside the black hole, and the energy emitted through Hawking radiation does not contain the information about the object. In other words, an object falling into a black hole doesn't entirely disappear, it exists in a stored state within the black hole. The specific form of existence inside a black hole has not been definitively clarified. Some scientists argue that a singularity exists inside a black hole, and the object is absorbed into this singularity. Others posit that there is no singularity inside a black hole, and the object spreads throughout the internal space of the black hole. This problem remains one of the yet-to-be-solved puzzles in physics. The scientific claims or theories regarding black holes serving as gateways for time travel, different dimensions, or other galaxies are as follows. Time travel using black holes. There is a proposition that the powerful gravitational field near a black hole could be utilized to achieve time travel to the future. This idea is based on Einstein's special theory of relativity, which explains that time for an object moving at speeds close to the speed of light passes more slowly than for a stationary object. The intense gravity near a black hole, which is so strong that even light cannot escape, would cause time near the black hole to flow much more slowly than in the external environment. Therefore, a spacecraft passing through the vicinity of a black hole might arrive in the future, from an external observer's perspective, after thousands or even billions of years have passed. Wormholes connecting black holes and white holes. The hypothetical concept of wormhole suggests that a virtual passage connecting black holes and white holes exists, allowing for travel to different spaces or times. Wormholes are theoretical pathways that enable rapid transit from one point in space to another. In this scenario, the entrance of a black hole is connected to the entrance of a white hole. Black holes act as objects that pull matter in, while white holes expel matter. Theoretically, through a wormhole, one could traverse to other galaxies, dimensions, or even different times if the entrances exist at different temporal points. However, Wormholes are considered highly unstable, and their lifespan is short. If a wormhole contracts, it would destroy everything passing through it. 3. Black hole singularity connecting to other dimensions. There is a hypothesis suggesting that the singularity at the center of a black hole, a point with infinite density and curvature, might be connected to other dimensions. The singularity is a region where the laws of physics, as described by general relativity, break down, requiring a theory of quantum gravity. According to some theories, the singularity may be linked to spatial dimensions other than the three we observe, and traversing a black hole could lead to other universes or dimensions. This hypothesis is related to theories like brane world theory or M-theory, which deal with higher dimensional spaces. It is important to note that these scientific claims or theories regarding black holes as gateways for time travel, different dimensions, or other galaxies have not been fully proven, and further research and discoveries are needed. This area remains speculative and unproven in scientific terms. Einstein and Rosen published a paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" in 1935. In this paper, they introduced the concept of a hypothetical passage called a wormhole, connecting black holes and white holes. A wormhole is a theoretical pathway that allows for rapid transit from one point in space to another, assuming that the entrances of a black hole and a white hole are connected. Black holes act as objects that pull matter in, while white holes expel matter. According to this theory, it was claimed that traveling through a wormhole would enable movement to different spaces or times. In other words, an object crossing the event horizon of a black hole could exit through the entrance of a white hole, potentially allowing for time travel. However, this theory has not been substantiated by scientific evidence. The existence of wormholes appears feasible under general relativity, but it encounters contradictions with quantum mechanics. Additionally, wormholes are highly unstable, and their short lifespan raises the possibility of destruction for anything passing through them. Therefore, the feasibility of time travel through wormholes remains unknown. The black hole information paradox refers to a contradiction between the predictions of general relativity and quantum mechanics regarding black holes. According to general relativity, black holes pull all matter and information beyond the event horizon. The event horizon is the boundary from which even light cannot escape. In contrast, quantum mechanics dictates that information must be conserved. Therefore, the fate of matter and information pulled into a black hole becomes a problem when the black hole evaporates, causing the event horizon to disappear. If all information inside the black hole is destroyed when it evaporates, it would violate the conservation of information law. On the other hand, if the information inside the black hole is preserved during evaporation, it implies the possibility of information moving beyond the event horizon, contradicting general relativity. In summary, the concepts of wormholes and the black hole information paradox remain speculative, lacking definitive scientific proof. The questions surrounding the feasibility of time travel through wormholes and the fate of information inside evaporating black holes are yet to be fully understood. Therefore, the black hole information paradox presents a fundamental challenge to our understanding of black holes. Various attempts have been made to resolve the paradox, but a definitive solution remains elusive. One proposed solution suggests that information swallowed by a black hole is preserved at the singularity. The singularity is a point at the center of a black hole where gravity is infinite and spacetime is highly warped. Since our known physical laws do not apply at the singularity, it is suggested that information could be conserved there. Another solution proposes that when a black hole evaporates, the information inside it is emitted in a copied form. Hawking radiation is the energy emitted when a black hole evaporates, consisting of various particles such as photons and neutrons. Therefore, the information absorbed by the black hole might be copied into these particles and emitted. While the black hole information paradox remains unsolved, it serves as an essential research topic to expand our understanding of black holes. The paradox revolves around the fate of information swallowed by black holes, challenging the application of both general relativity and quantum mechanics to black hole scenarios. The paradox emerged in 1974 when Stephen Hawking presented his paper on Hawking radiation. This phenomenon suggests that black holes eventually disappear as they emit copied energy, causing a reduction in mass. Hawking initially claimed that the information absorbed by the black hole would also be annihilated in this process. However, the conservation of information law dictates that information cannot be destroyed. Thus, Hawking's assertion that the information within the black hole is entirely annihilated contradicts the information conservation law. The black hole information paradox remains an unresolved mystery. The question of whether one of the laws needs to be abandoned or if a new set of physical laws that satisfies both can be discovered remains unanswered. The resolution of the black hole information paradox holds significant implications for our understanding of the fundamental laws of the universe. Its resolution could lead to substantial progress in our comprehension of the nature of the cosmos. Several possible solutions have been proposed to resolve the black hole information paradox. Information is emitted through Hawking radiation, Hawking copying, but remains at the singularity. This solution satisfies the conservation of information law but contradicts observational results of Hawking radiation. Information is emitted through Hawking radiation and reconstructed at the singularity. This solution aligns with observational results of Hawking radiation but violates the conservation of information law. The combination of general relativity and quantum mechanics is incorrect. This solution implies the need to discover new physical laws. The definitive answer among these solutions has not yet emerged. It is expected that future research will contribute to resolving the black hole information paradox. The black hole information paradox arises from the apparent contradiction between general relativity and quantum mechanics in explaining black holes. According to general relativity, black holes create singularities in spacetime, trapping anything that enters them forever. In contrast, quantum mechanics dictates that information must be conserved, suggesting that information from objects entering a black hole should be preserved somewhere. Combining these theories leads to the conclusion that information from objects entering a black hole must be conserved within the black hole's interior. However, the interior of a black hole is an area where the known laws of physics do not apply, making it unclear how information is preserved. The black hole information paradox remains an unsolved problem, and resolving it may require the development of new physics laws that integrate general relativity and quantum mechanics. The black hole information paradox can be divided into two hypotheses. Information is destroyed. This hypothesis suggests that information within a black hole is destroyed, meaning that when a black hole evaporates, the information of objects it absorbed is permanently lost. This contradicts the conservation of information law and is not widely accepted by physicists. Information is preserved. This hypothesis proposes that information within a black hole is preserved in some form. Consequently, when a black hole evaporates, the information of the absorbed objects returns to the universe in some way. While this adheres to the conservation of information law, an explanation is needed for how information is preserved within the black hole's interior. The black hole information paradox remains one of the most significant challenges in cosmology. Resolving this paradox may necessitate the development of new physical laws, possibly involving quantum gravity or other theoretical frameworks. In the cosmic tapestry, where black holes dance, a mysterious rhythm, a celestial trance. Gravity's grip, a cosmic embrace. Bending the fabric of time and space. On the event horizon, where light takes a bow. Whispers of secrets, only the cosmos can endow. Time travel's mirage, a tantalizing notion. A voyage through epochs, a poetic potion. Through the wormholes of uncertainty we delve. Into the past, future, where mysteries swell. The horizon's paradox, a puzzle unsolved. In the vast universe, our questions evolved. Celestial bodies, storytellers of the night. Witness to eons, in their silent flight. The enigma of existence, a timeless quest. In the cosmic symphony, we are but a guest. Parallel universes, mirroring our plight. In the grand theater of the infinite night. Beyond the stardust, where dreams and reality blend. We chase the echoes of time, around the cosmic bend. So, let us marvel at the black hole's eye, where the past and the future entwine and fly. In the celestial theater, where mysteries unfold, we dance with the cosmos, in a story yet untold.
In the cosmic abyss, the weight of black holes. A wondrous chronicle of time, an era that unfolds. Strokes of light, the touch of darkness. Mysteries embedded in the past, secrets of the future's harness. The cosmic dance floor, a ballet of starlight. Silhouettes of time, our steps in the night. A dazzling night sky, a stage of enigma. We are but a chapter in the living universe's drama. Today, I will introduce an alternative theory to resolve the paradox of black hole information, known as the holographic principle. This principle, independently proposed by Gerard T. Hooft and Leonard Susskind in the 1990s, suggests that the event horizon of a black hole plays a role similar to a hologram. In holography, a two-dimensional surface encodes a three-dimensional image. Observing the surface of a hologram allows us to perceive a three-dimensional image. According to the holographic principle, the event horizon of a black hole is analogous to a two-dimensional surface. This surface encodes all the information generated within the black hole's interior. The holographic principle is considered crucial in resolving the paradox of black hole information. This paradox arises from the contradiction between the need to preserve information of objects falling into a black hole and the fact that information cannot escape from the black hole's interior. According to the holographic principle, all information generated within a black hole is encoded on the event horizon. Therefore, when a black hole evaporates, the information encoded on the event horizon returns to the universe. The holographic principle posits that spatial volume can be considered an encoding of information on lower dimensional boundaries, such as the boundary of light. This principle is a theoretical postulate of string theory and a presumed property of quantum gravity. In the context of black hole theories, the holographic principle plays a significant role. The event horizon of a black hole is considered a two-dimensional surface. According to the holographic principle, all information within the black hole is encompassed on this two-dimensional surface. The holographic principle holds promise in resolving the paradox of black hole information. If all information of a black hole is encoded on a two-dimensional surface, then when the black hole evaporates, this information can return to the universe through that two-dimensional surface. ADS, CFT duality. ADS, CFT duality, proposed by Juan Maldacena in the 1990s, represents a duality between a five-dimensional anti-de Sitter space, ADS space, and four-dimensional conformal field theory, CFT. ADS space is a five-dimensional space with negatively curved spacetime, while CFT is a quantum field theory occurring in four-dimensional spacetime. This duality plays a crucial role in understanding the thermodynamics of black holes. Black holes are considered to play a role similar to the boundary of ADS space in the context of ADS-CFT duality. Therefore, using ADS-CFT duality, we can gain insights into the thermodynamics of black holes. ADS-CFT duality is closely related to the holographic principle. According to the holographic principle, the volume of three-dimensional spacetime can be encoded on a two-dimensional surface. ADS-CFT duality provides a method to implement such holograms. While ADS-CFT duality is not fully understood, it is believed to play a significant role in the future study of black hole theory. ADS-CFT duality corresponds to the relationship between anti-de Sitter, ADS, space and conformal field theory, CFT. ADS space is a five-dimensional spacetime with negatively curved geometry, and CFT is a quantum field theory with a four-dimensional boundary. ADS-CFT duality serves as an example of the holographic principle. The information in ADS space corresponds to the information in CFT. Thus, ADS-CFT duality aids in explaining the holographic principle in black hole theories. ADS-CFT duality can also assist in resolving the paradox of black hole information. According to ADS CFT duality, information within a black hole is contained in AD space. Consequently, when a black hole evaporates, this information can be transmitted to CFT through AD space. The significance of the holographic principle in ADS CFT duality and black hole theory. The holographic principle and ADS CFT duality play crucial roles in black hole theory. These principles can potentially help resolve the paradox of black hole information. Additionally, they may aid in understanding the internal structure of black holes. While the holographic principle and ADS CFT duality remain theoretical and not completely understood, they are expected to have a substantial impact on the future research of black hole theory. The holographic principle and ADS CFT duality are two fundamental concepts in black hole theory. The holographic principle suggests that information in three-dimensional space can be encoded on a two-dimensional surface. This principle was discovered in the early 1990s as scientists explored the thermodynamics of black holes. Black holes, as gravitational anomalies in spacetime where nothing can escape, are known to emit heat. Researchers studying the thermodynamics of black holes found that the entropy of a black hole is proportional not to its volume but to the area of the event horizon. This implies the existence of infinite information inside a black hole. According to the holographic principle, this infinite information can be encoded on the two-dimensional surface of the event horizon. In other words, all information within a black hole can be observed through the two-dimensional surface of the event horizon. ADS CFT duality is a form of holography that deals with the correspondence between a three-dimensional quantum field theory CFT and a five-dimensional anti-de Sitter space AD space. Discovered by theoretical physicist Juan Maldacena in 1997, this duality suggests that the information in a three-dimensional quantum field theory can be viewed as existing on the boundary of a five-dimensional AD space. ADS CFT duality is closely related to the holographic principle. In ADS CFT duality, the quantum field theory in three-dimensional space is considered as being on the boundary of a five-dimensional space. Therefore, information in the three-dimensional quantum field theory can be encoded on the boundary of the five-dimensional AD space. In the context of black hole theory, the holographic principle and ADS CFT duality are believed to be crucial in resolving the paradox of black hole information. According to these principles, information within a black hole is encoded on a lower dimensional surface, allowing for a potential understanding of the fate of information when a black hole evaporates. Both the holographic principle and ADS CFT duality hold promise for advancing our understanding of the enigmatic nature of black holes and their underlying physics. According to the holographic principle, all information within a black hole can be encoded on the two-dimensional surface of the event horizon. Therefore, the paradox of black hole information can be resolved by explaining how the two-dimensional surface of the event horizon changes when the black hole evaporates. ADS CFT duality signifies a correspondence between a three-dimensional quantum field theory and a five-dimensional quantum field theory. Thus, it is possible to model the information inside a black hole with a three-dimensional quantum field theory. It is expected that through this modeling, new methods for resolving the paradox of black hole information can be discovered. Both the holographic principle and ADS CFT duality are concepts that are not fully understood yet. However, these two concepts are believed to play crucial roles in black hole theory. Further research is expected to deepen our understanding of these concepts. The holographic principle and ADS CFT duality are both essential concepts in black hole theory. The holographic principle proposes that the volume of three-dimensional spacetime can be encoded on a two-dimensional surface. This principle is considered crucial in resolving the paradox of black hole information. ADS CFT duality involves a duality between a five-dimensional anti-de Sitter space AD space and a four-dimensional conformal field theory CFT. This duality provides a relationship between the thermodynamics of black holes and quantum field theory. The holographic principle and ADS CFT duality are related to the simulation theory. Simulation theory posits that the universe we inhabit might be a computer simulation. While this theory is not scientifically proven, it has captured the interest of many people and has been explored in science fiction. According to the holographic principle, the three-dimensional volume of spacetime can be encoded on a two-dimensional surface. Although the method to implement such holograms is not yet known, computer simulation could potentially achieve this. ADS-CFT duality provides a relationship between the thermodynamics of black holes and quantum field theory. This connection can be utilized in simulating black holes through computer simulations. Therefore, the holographic principle and ADS-CFT duality can be interpreted as evidence supporting simulation theory. Of course, whether simulation theory is correct remains unknown and unproven scientifically. It is a hypothesis suggesting that our universe is a computer simulation, and the holographic principle and ADS-CFT duality offer theoretical bases that align with this idea. Simulation theory suggests that the universe we live in might be a computer simulation. While this theory lacks scientific evidence, it has become a popular theme in science fiction movies and novels. The holographic principle and ADS-CFT duality can be presented as evidence supporting simulation theory. According to the holographic principle, the three-dimensional volume of spacetime can be encoded on a two-dimensional surface. This principle might imply that our universe, following the holographic principle, could be a three-dimensional world generated from a two-dimensional surface in a computer simulation. ADS-CFT duality also aligns with simulation theory. According to this duality, the quantum mechanics of a five-dimensional space is equivalent to the quantum field theory in a four-dimensional space. This principle might suggest that our universe, according to ADS-CFT duality, could be a simulation with hardware and software components. The holographic principle and ADS-CFT duality are concepts that are not fully understood yet, but they can be presented as theoretical evidence supporting simulation theory. Simulation theory proposes the hypothesis that the universe we inhabit is a computer simulation. This idea remains unproven scientifically but has inspired various science fiction works. The holographic principle and ADS-CFT duality can be seen as providing evidence supporting simulation theory. According to the holographic principle, the three-dimensional volume of spacetime can be encoded on a two-dimensional surface. This principle implies that our universe might be a simulation, where the information of the three-dimensional world is encoded on a two-dimensional surface. ADS-CFT duality is also relevant to simulation theory. It suggests an equivalence between the quantum mechanics of a five-dimensional space and the quantum field theory in a four-dimensional space. This idea may indicate that our universe, following ADS-CFT duality, could be a simulated reality with specific rules encoded in its structure. While the holographic principle and ADS-CFT duality are not fully comprehended, they can be interpreted as theoretical foundations supporting the concept of simulation theory. According to the holographic principle, the three-dimensional volume of spacetime can be encoded on a two-dimensional surface. Following this principle, all the past and history of humanity could potentially be encoded on the event horizon of a black hole in the form of infrared radiation, neutrons, or other forms of energy. Of course, this is still a hypothesis, and extensive research is needed to resolve the information paradox of black holes. However, if true, black holes could serve as colossal databases storing the history and culture of humanity. When a black hole evaporates, this information might return to the universe. While this possibility is fascinating, it remains speculative until further investigation occurs. The straightforward answer to this question is, yes. Black holes are places where spacetime is severely warped, and nothing can escape, potentially allowing for the storage of all of humanity's past and history. However, a more nuanced response is, perhaps, the information stored in a black hole must adhere to known physical laws. Therefore, even if all of humanity's past and history were stored in a black hole, it might not be encoded in a way that we can read or understand. Information stored in a black hole could take various forms. Infrared and neutrinos. Particles like infrared radiation and neutrinos can pass through a black hole. Therefore, all of humanity's past and history could be projected onto these particles and encoded in a black hole. 2. Quantization of information. Information is quantized, divisible into minimal units known as bits. Even if all of humanity's past and history were stored in a black hole, it might be divided into extremely small units. Holographic principle. According to the holographic principle, three-dimensional information of spacetime can be encoded on a two-dimensional surface. Humanity's past and history might be holographically stored on the event horizon of a black hole. None of these hypotheses have been scientifically proven, but they provide essential clues for resolving the information paradox of black holes. If the holographic principle holds, the three-dimensional volume of spacetime can be encoded on a two-dimensional surface. According to this principle, all of humanity's past and history could be stored as a hologram on the event horizon of a black hole. This hypothesis is still speculative, and resolving the information paradox of black holes requires further research. The question of whether all of humanity's past and history is encoded in a black hole remains an open topic for future investigation. Several hypotheses exist regarding the information paradox of black holes. Information destruction. This hypothesis suggests that information within a black hole is destroyed, meaning that when a black hole evaporates, the information of objects it consumed is lost forever. Many physicists find this hypothesis problematic as it violates information conservation laws. Information preservation. This hypothesis posits that information within a black hole is preserved. Consequently, when a black hole evaporates, the information of objects it consumed returns to the universe in some form. While compliant with information conservation laws, this hypothesis lacks a clear explanation of how information is preserved within a black hole. Information transference to another dimension. This hypothesis proposes that information within a black hole is transferred to another dimension. When a black hole evaporates, the information of consumed objects might manifest in a different dimension. Although lacking scientific evidence, this idea remains intriguing. The fate of information inside a black hole is yet to be fully understood, and these hypotheses contribute to ongoing efforts to resolve the information paradox. The paradox of the black hole, the paralysis of information. A symphony of simulation, the echoes of the final judgment. Worlds where gateways open to dimensions untold. A cosmic intersection where reality and dreams unfold. The cosmic pathway leading to portals. Endless alleyways of spacetime's stellar corals. A realm where existence and non-existence entwine. A labyrinth of information, a puzzle in the design. Within the gaze of the black hole, distortion of time. The chaotic moment nearing the ultimate truth of the cosmic prime. Thrills in the multiverse, the faint future of judgment. Our destiny shrouded in mysteries profound and abundant. Dreams scattered at the infinite gateway. A nostalgic journey into the embrace of the cosmic array. The information of the black hole, the paradox of dimensions. In the cosmic puzzle, we encounter profound revelations.
The paradox of the black hole, the paralysis of information. A symphony of simulation, the echoes of the final judgment. Worlds where gateways open to dimensions untold. A cosmic intersection where reality and dreams unfold. The cosmic pathway leading to portals. Endless alleyways of spacetime's stellar corals. A realm where existence and non-existence entwine. A labyrinth of information, a puzzle in the design. Within the gaze of the black hole, distortion of time. The chaotic moment nearing the ultimate truth of the cosmic prime. Thrills in the multiverse, the faint future of judgment. Our destiny shrouded in mysteries profound and abundant. Dreams scattered at the infinite gateway. A nostalgic journey into the embrace of the cosmic array. The information of the black hole, the paradox of dimensions. In the cosmic puzzle, we encounter profound revelations. Today, in the 18th lecture of the Introduction to Astronomy, Part 3 of the Black Hole series, we will discuss the hypothesis of the ultimate judgment and the paradox of time travel through wormholes. The idea that black holes could be the site of the ultimate judgment has been debated in religious and philosophical contexts for a long time. According to this hypothesis, black holes serve as repositories of all information in the universe. Therefore, during the ultimate judgment, everyone would be summoned to a black hole to undergo judgment for their lives. This hypothesis is supported by the following arguments. Black holes do not violate the law of information preservation. Thus, the information of objects falling into a black hole must be preserved somewhere. Black holes are like rifts in spacetime, and nothing can escape from them. Therefore, during the ultimate judgment, everyone would inevitably be summoned to a black hole to face judgment. While this hypothesis has not been scientifically proven, it provides important clues to the paradox of information within black holes and the ultimate questions regarding judgment. It's important to note that this hypothesis holds significance mainly from a religious perspective. Scientifically, there is no evidence supporting black holes as the location for the ultimate judgment. In Christian theology, the ultimate judgment involves the dead being judged before God, with the righteous entering heaven and the wicked going to hell. The hypothesis that black holes could be the site of the ultimate judgment offers the following arguments. Black holes, being rifts in spacetime, are suitable as a place where the dead are judged before God since nothing can escape from them. Black holes could store all information, enabling the recording and evaluation of the actions and thoughts of the deceased. While this hypothesis has not been scientifically substantiated, it is considered an intriguing idea that aligns with religious beliefs. The following are religious beliefs supporting the hypothesis that black holes could be the site of the ultimate judgment. In Christianity, God is considered a transcendent being beyond spacetime, implying the ability to traverse rifts in spacetime, such as those associated with black holes. The ultimate judgment in Christianity is seen as fair and just for everyone. Since black holes store all information, they could accurately evaluate the actions and thoughts of all individuals. While these beliefs lack scientific proof, they can be presented as supporting evidence for the hypothesis that black holes are the site of the ultimate judgment. According to this hypothesis, black holes serve as repositories for the souls of all humans. After death, each soul would reach a black hole to undergo judgment for their lives. This hypothesis is based on the following arguments. Black holes, being rifts in spacetime, would prevent the escape of souls after death. The strong gravitational force of black holes could attract the souls of all humans. Black holes adhere to the law of information preservation, indicating that information about all human souls would be stored within them. While this hypothesis lacks scientific proof, it is considered an interesting idea within the context of religious beliefs. Here are some specific descriptions of the hypothesis that black holes could be the site of the ultimate judgment. The event horizon of a black hole is the location of judgment. Each human soul undergoes judgment as it crosses the event horizon, facing the consequences of their life. The singularity of a black hole is the seat of judgment. Every human soul encounters God at the singularity, facing divine judgment. Hawking radiation from a black hole determines the judgment outcome. Each human soul is emitted through Hawking radiation, leading them to either heaven or hell. While these descriptions lack scientific basis, they evoke intriguing imagination and are related to religious beliefs. If a wormhole exists and one briefly stays there, gaining information about the future, and then returns through the wormhole to the present, the observed future may change. There are two ways to resolve this paradox. The first method assumes non-linearity of time. Non-linearity suggests that the flow of time is not linear, and the future can influence the past. According to this assumption, the act of obtaining information from the future in the past can indeed alter the future. Therefore, upon returning to the present after glimpsing the future, the seen future would have already changed. The second method involves assuming the existence of parallel universes. In this scenario, parallel universes separate from our own exist. Following this assumption, after returning to the present from seeing the future, one would have observed the future of a different universe. Therefore, the seen future is unrelated to the future of the universe we inhabit. It is still uncertain which of these two methods is more valid. However, assuming the existence of wormholes, one of these methods would need to be adopted to resolve this paradox. The first method is somewhat innovative in introducing the concept of non-linearity of time. Nevertheless, scientific evidence for the actual existence of non-linearity of time is currently lacking. The second method is relatively conservative by introducing the concept of parallel universes. However, scientific evidence for parallel universes is also lacking, although quantum mechanics does not rule out the possibility of their existence. In conclusion, assuming the existence of wormholes, further research is needed to resolve this paradox. If wormholes exist, the paradox can be addressed through methods such as multiverse theory. This theory proposes the existence of multiple universes, and if one can travel through a wormhole to another universe, it would be possible to see that universe's future. In this case, changes in the present future would be the result of alterations in the future of a different universe, avoiding paradox. Non-linearity of time. This theory posits that time is not linear, and actions in the past can affect the future. If information obtained through a wormhole influences the present future, it would prevent paradoxes. Information destruction. This theory suggests that even if one gains information about the future, the inability to comprehend or remember that information might prevent changes in the future. While these theories have not been scientifically proven, they provide potential solutions to the paradox if wormholes exist. I personally think that the multiverse theory is the most plausible among the options. This theory has already gained support through research conducted by various scientists. If wormholes exist and one can gain information about the future through them, paradoxes can arise. To address these paradoxes, the following hypotheses are possible. Multiverse of information. According to this hypothesis, the universe is composed of an infinite number of multiverses. Therefore, when returning to the present after glimpsing the future through a wormhole, if the future has changed, it might have occurred in a different multiverse. Nonlinearity of quantum mechanics. Quantum mechanics exhibits nonlinear characteristics, where small changes can lead to significant outcomes. Thus, if the future changes upon returning to the present after obtaining information, it could be due to small changes triggered by our observation of the future. Time reversal. If time reversal is possible, changes in the future upon returning to the present after perceiving future information might be attributed to us reversing the flow of time by observing future events. None of these hypotheses have been scientifically proven yet, but they are presented as possible solutions to these paradoxes. Personally, I find the multiverse of information hypothesis to be the most plausible. This is because the nonlinearity of quantum mechanics is still not fully understood, and time reversal could potentially violate physical laws. However, it's important to note that none of these hypotheses have received scientific confirmation. Therefore, how these paradoxes are resolved will likely be revealed through future research. Through the fragrant path of a journeying wormhole. Peering into the doors of the future unfold. Multiverse smiles, the dance of quantum's play. In the cosmic expanse, where time has its say. The road of spacetime, a branching trail. Embracing futures in the multiverse's kale. The whispers of an ancient mystery once heard. Trapped in the wormhole, where time's secrets stirred. Multiverse's grin, quantum's graceful dance. A universe of information, a time-traveling trance. A path through time, a crossroads so grand. Holding the futures of the multiverse in hand. Once a dream of old, a fantastical lore. Caught in the whispers of a wormhole's core. Multiverse of joy, the quantum sublime. A celebration of time within the cosmic chime. The road of spacetime, a branching affair. Guardian of futures, the multiverse's care. Parallel tales, quantum's sweet song. A moment in a wormhole, where light belongs. Information's multiverse, a quantum dream. Peering into the future's door, a fragrant beam.